We continue with the stiffness method for continuous beams. The objective that we're working on is how to apply the stiffness method to beams with NOK greater than 1. In the previous video, we already saw how to determine DOFs and draw deformed shapes. We saw how to use appendices C and D, and now we'll be looking at the matrix formulation of the stiffness method. That is, how do we take all that preliminary information that we computed already and combine it so that we can get our answer. Our main task is going to be calculating equilibrium at each degree of freedom. On the left-hand side, I've shown the free body diagrams from the previous work that we did for degree of freedom 1, 2, 3, as well as for the applied load. Now, in the actual structure, all of these are acting at the same time. Degree of freedom 1, the left-hand node, can rotate at the same time that degree of freedom 2, the center node, can rotate. At the same time that degree of freedom 3, the right-hand node can rotate. And of course, this all happens as the applied load is in place. So all of these actions apply at the same time. At any instant of time, the moments on each degree of freedom must be in equilibrium. Let's do equilibrium calculations. Taking the normal sign convention that we take, counterclockwise positive, and let's look at these degree of freedom by degree of freedom. Let's look at the forces at degree of freedom 1 in all of these different cases. If I sum at degree of freedom 1, I have M1 with the negative sign because it's acting clockwise times a scaling factor. Recall that M1 was obtained for a unit rotation, but what actually occurs is a rotation of unknown magnitude that we call theta 1. For degree of freedom 2, we have M2 with a negative sign times its scaling factor. For degree of freedom 3, there are no forces shown for degree of freedom 3, so we show 0. For completeness, we'll multiply that by the scaling factor. And then for the applied load, we have M3 acting in the clockwise direction, or again, negative. Moving to degree of freedom 2, now we'll be adding up all of the moments on the center node during all of these actions occurring simultaneously. So once again, moving from top to bottom. At the top, we have M2 acting clockwise with the negative sign times the scaling factor. At the center node, we have M1 acting twice clockwise times the scaling factor. For degree of freedom 3, we have M2 with the negative sign because it's clockwise times the scaling factor. For the applied load, we have M3 in one direction and M3 in the other direction, which balance out to 0. Now we move on to the forces acting at degree of freedom 3 in all of these situations at the same time. There's no force for the top diagram. There's a scaling factor that we put in for completeness. M2 on the second diagram acts in a clockwise or negative direction times the scaling factor. In the third diagram, M1 acts in the clockwise direction times the scaling factor. In the last diagram, M3 acts counterclockwise or positive. Now, this problem is solvable. M1, M2, and M3 can be calculated. M3 we already calculated. M2 and M1 have to do with EI, which was given, albeit symbolically, and L, which is 20 feet. The unknowns are theta 1, theta 2, and theta 3. We have 3 equations, 3 unknowns, so we know we can solve it. What we'll do in the subsequent steps is see how we can arrange this in a matrix form to make the solution quicker. So these are the equations that we determined previously. Now, what we want to do is we want to write this in matrix form. What I'll do is I'll take all of these quantities here, move them over to the other side of the equation, and in doing so, I'm going to swap all the signs. So the negatives will become positives, the positives will become negatives. I can obtain the following relation in matrix form. We'll notice these quantities here are simply repeated down here. If we recall how we multiply matrices, the M1 gets multiplied by the theta 1, the M2 gets multiplied by the theta 2, and the 0 gets multiplied by the theta 3. This corresponds to the first row right here. Looking at just one more example to convince ourselves that this is really saying the same thing, let's look at the third row. The 0 is multiplied by the theta 1, the M2 is multiplied by the theta 2, and the M1 is multiplied by the theta 3, which tells us the same as the third row there. What we've accomplished here is writing the equations in a much more compact form that's easier to solve by just giving the matrix and the vector to a computer and getting the unknown thetas. We'll now say a little bit more about each of these matrices and vectors and define them a little bit more formally. We'll start with the U sub j. That's the displacement at each degree of freedom, at the jth degree of freedom. And as in other parts of this course, we're using the term displacement generally to mean either a linear displacement or a rotation. The stiffness matrix, Kij, is the force at the ith degree of freedom due to a unit displacement at the jth degree of freedom. We'll have a positive sign convention that'll become more relevant later, and that is that the Kij is positive if it resists the ith degree of freedom. That is the blue arrows that I'm drawing. Here as well, the term force is used generally to mean either a linear force or a moment. The vector p sub I is the applied force at the ith degree of freedom. It's going to be positive in the direction of the ith degree of freedom. We also call this the load vector. This vector p sub I comes from fixed end forces due to member loads, as we saw already, and forces applied directly at the nodes, which we haven't done yet, but we'll do so in subsequent examples. Now we can interpret the stiffness matrix further. So here again, I'm showing the stiffness matrix, and I'm showing the definition. What I'd like to look at is what each of the columns means and what each of the rows means. Let's start with the columns. So each column refers to a different displaced shape. The first column refers to this displaced shape, the second column refers to that displaced shape, and the third column refers to this displaced shape. Each row refers to a different location. So for instance, this value here, 2m1, that tells me what is the force at the center node due to a displacement used generally, or due to a rotation at the center node. This term right here in the upper right hand corner tells me what the force is at the left hand node due to a rotation at the right hand node. The physical interpretation of rows and columns of the matrix are consistent with the use of the I and J subscript. This will become more clear later, especially because in subsequent problems we'll use this interpretation to form the stiffness method directly. So if you don't fully get this yet, don't worry, we'll be working this topic quite a bit more as we develop our later examples. Let's see how we solve this matrix problem for the unknown vector of rotations. The K, or stiffness matrix, is all known. M1 and M2 have to do with EI and L, which are known. The load vector is known. M3 we previously calculated and got numerical values for. So what's unknown is the displacement vector, U, which consists of all the nodal rotations. We know that P equals KU, so U is equal to K inverse P. Please never calculate the inverse of a matrix by hand or even on your calculator. This is what we have computers for. This is not intended on being a difficult part of this class. Compute the inverse, multiply by the load vector, and we get the following vector for the unknown nodal rotations. I've factored out an L over EI, I've factored out the units kip feet, and then I have the computed number inside. This might be a good exercise to do at home. Plug in 1 for EI and see if you can reproduce the same numerical answer. Let's talk about what this means physically. U1 is minus 16.7 L over EI kip feet. We use the same sign convention as we did for our moments, so counterclockwise is positive. Because U1 is negative, that means that U1 acts clockwise, and that's what I've shown in the diagram. U2 is 0. That means that this center node does not rotate. That makes sense because the original problem was symmetric. The value for U3 is positive, same magnitude as U1, so positive means counterclockwise, so the rotation U3 is counterclockwise. So what the solution tells us at this point is what all of our nodal rotations are. Let's summarize what we have so far. We first drew each of the degrees of freedom, and we determined the member forces. Going forward, we're not going to explicitly consider equilibrium at each degree of freedom. We're going to form the stiffness matrix directly according to the definition. So we haven't seen that yet, but that's what we'll see going forward. Third, we'll form the load vector from the member nodal forces, again directly according to the definition instead of explicitly considering equilibrium at each node. So right here, these two steps imply equilibrium, and this example was intended to show you that very explicitly, but going forward that's going to be pushed into the background a little bit. Step 4 is to calculate the vector of unknown displacements, u is equal to k inverse p, and going forward in a subsequent video, we'll determine the member forces. We'll look at two different methods, and it's nice to have two different methods at your disposal because sometimes one will be easier than another. And these two methods are 1, scaling and adding the member forces for each degree of freedom, and 2, using a new set of equations to get the member forces directly from the calculated displacements. So next time, we'll work on determining the member forces.